9, 10, 11. We'll start with 9. It's all larger. This will be fast. Everyone, I want you to take a counterclockwise oriented circle wherever you want in this vector field. You want to start right here? Which way is counterclockwise? No. Just go around this way. I want you to tell me, would this answer be positive, negative, 0, or unable to be determined?
Positive.
What do you think?
Positive.
Positive? Does everyone agree? Why is the answer positive? Because when I take a counterclockwise circle, I'll start right here. In this vector field, all these vectors were going in the same what? Direction as my path. Does that make sense? Cool. They said a full counterclockwise circle. We could have done just a half circle, right? As long as it's counterclockwise. All right? Let's go to number 10. It goes fast, though. Hey, go to number 10. And when we're done, I might add one on the board. Evan, enlarge this. You got to go from the point negative 4, 4 to 4, negative 4. Will you mark those? Where's negative 4, 4? Negative 4, 4 is here. And you got to go to 4, negative 4. So you got to start here and go along that path. What do you think the answer is?
0.
Very good. The answer, the line integral would be 0. At the time they were, and you notice I did on purpose, took a straight line path so it was very obvious. That would come out to be an answer 0. How about number 11? You got to go from 3, 3 to 0, 0. All right, where's 3, 3? Told you this goes quick. It's fun too. 3, 3 right there. Go from here, and the path is going towards the origin.
Negative.
What do y'all think?
Negative.
It's going to be negative. Does everyone see all the vectors we're going against you along that path? Cool. That's it. I do want to add one on the board, though, to this. So I'll turn this off. There's no other images I want to see. Very good with that. So now when you can find this, they call this work. The work done by a vector field to move a particle along the path C. That's what this is referred to. Not the line integral of a scalar function, but the line integral of a vector field is referred to as the work done by the vector field to move a particle along path C. What was work equal to before? Force times what?
Distance.
Force times distance. We got this F dot dr. So you remember we said like F dot d? Back in, gosh, it was chapter 12. I'll hit the light. You all remember that? So that's why this actually comes out to be the work done by the vector field. It was like, we said, this was work. Now look at the vector field. So this is the work done by the vector field. I'll put work. It equals line integral of a vector field. We got the C here. What's the notation? F, not the ds, but a dot dr. And we'll work some problems. The first one I wanted to do is this. What if you did a circular path along a vector field like this? I should have added one more to that practice problem I had in the image. That's okay, I'll put it on the board right now. And what if a vector field, we saw a vector field like this earlier today. Do you remember? Did we see a vector field like this earlier today? Yeah, it was something like this. Vector field of x comma y. Okay. I was just wondering, what if you took a counterclockwise path along here? What do you think you'd get?
Nothing.
You go, all right, everyone, I'll take my circle right here. Here's my circle path. What do you notice? We're summing dot products, right? So if I go in this direction, what's going on? What do you think the dot product of that vector with that vector is? 0. Why? Because the dot product of two perpendicular vectors is?
0.
0. What would happen like right here? I'm going along this path. The dot product with that and that. So what do you think would come out of this?
0.
Yes. You should get a line integral. If you took an entire counterclockwise path, this was your vector field, x, y, and they talk about, you know, the path being a full circle. Well, you're just going to sum up a bunch of zeros. Cool? So that's another one I should add to that. Because sometimes you go, well, what if it's totally perpendicular? The dot product 0. You're just summing a bunch of zeros. All right. So, I'm glad you know this. Work can come out positive, work can come out negative, or work can come out to be what? 0. And it all depends how many vectors are going against, or going with, etc. All right, let's work one. So, which one I thought was good from the practical problems? I like, we'll do 3 of these. Let's do number 12. 3 of these we do. Number 12 says this. Evaluate. Line integrals, got the C there. F dot dr. So you know it's evaluating the line integral of the vector field. Now they gave the vector field. Here's the vector field. F is, it's vector field, y, it's all very good. The vector field is y squared for the I component plus x minus y for the j component. Okay. Where's C? So they got to give you two things here. They got to give you the vector field and the curve. What's C? C is the curve, and is represented by, sometimes they write x equals this, y equals that, like before. In this case, they just wrote r of t, like a vector curve. 2t plus 1, 3t plus 2, and they want you to go from t equals 0 to t equals 1. And we'll evaluate this. Now, is the answer positive or negative? I don't know. Right? We'd have to visualize it. We need to make the vector field with Mathematica, Maple, Windplot or something just to get an image idea, but I don't know right now. Let's go to work. We'll find out. 0 to 1. It starts out with f dot dr. Now, what does this mean? We're going to do from some a to b, which is 0 to 1, f composed of RT, vector field composed of RT, and take the dot product with R prime at T. Alright. So, what is vector field composed of RT? Well, that's a y squared. What do I substitute for that y? Someone see it?
3t plus 2.
3t plus 2 gets substituted in there. That's what they mean, f composed of the r. Alright, so I'll put 3t plus 2 and put a square. What goes here? Oh, it looks like I might need a little more room. It has an x minus a what?
What?
What gets substituted there? That's not.
2t plus.
X minus y. Maybe I should write it all out. 2t plus 1 subtract.
3t
I gotta
minus
screw,
2.
Brad, I'm gonna screw this one up on purpose. Because this is the common error on the test. Do you see it?
Minus 2.
Does everyone see it? I've screwed up. This is a common error where you're just like that minus that, and you gotta screw that minus. So this would become a what? Minus 2, unless you want to put the parentheses. So there's f, composed of RT. Dot product with R prime. And hopefully you find R prime pretty easy.
2
Nothing
and,
crazy. What's that derivative?
2 and 3.
A 2, and that derivative is a
3.
then when there's x prime and t, there's y prime. So this is like that last problem we did with dx dy. This is a line integral of a vector field. Well, we'll find out, is this answer positive or negative? Hey, let me clean that up first. What does all that do? 3t plus 2 squared. That's what, negative t minus 1?
Mm-hmm.
Cool. So then all you got to do is, you know, with the dot product, 2 times this plus 3 times this. Okay. And what's 9t squared plus 6t plus 4 multiplied to a 2 plus negative t minus 1 multiplied to a 3. Let me do it again. I know it's not too bad. 18t squared plus 12t plus 8 minus 3t minus 3. So far so good. Any like terms in there?
Well, hold on a second. Did you do the dot product on this?
Yeah, when I did this, I did
Okay.
this times the 2 plus this times the 3.
3, okay. You just separate, okay.
Awesome. So Art okay with that?
Yeah.
Oh, awesome. Everyone okay with that with the dot product? Very good. In terms of what I did for the dot product, there's that dot. Let me make it big. This times this plus this times this.
Wouldn't 3t plus 2 squared be 9t squared plus 12t?
Oh yeah, so 9t squared plus such, because you got to distribute that too. You're the best. That'll be 18t squared plus the 12t.
So it's just 24 instead of 12.
Yeah, so right here. So when I was foiling this, 3t squared plus 6t plus 6t, Rach, thanks. She's like, that'll actually be 12t when I pull that, right? Making this now what?
24.
24. Rach, thanks again. I got the 18 and the 8 right, but you should be careful when you FOIL that. Any like terms in there? Yeah, you got 18t squared, now what? What's 24t minus 3t?
21t,
And 8 minus 3 is?
5.
But now I can tell, and we're going to evaluate this, this is coming out positive. So do you agree along this path? That's a straight line, by the way. You all recognize that? Does anybody recognize this curve? A curve. That's actually a line. There's no t-squareds in it. That's a line. Along that line, it looks like most of the vectors were going in the direction of the what? Of the path. Right? The stuff we can't see right now. But we can tell this answer is coming out positive. There's no negative right now. Oh, what's that integral? 6t cubed over 3? I mean 18t cubed over 3 is 6t cubed. Plus 21t squared over 2 plus, that's a 5, plus 5t. And you go from 0 to 1, I get 6 plus 21 over 2 plus 5. All right, what's 11 plus 10.5? That's 11 plus, what is that, 10.5? Is that 21.5? What's that as a fraction? 43 halves. So 21.5 or 3 halves. That's the work done by the vector field to move the particle along that curve or that path. Does that make sense? Hey, 2 more. First of all, I did want to point out, like I was saying before, that's a line, isn't it? I can recognize lines if it doesn't have t squareds in it. This surely could have had t cubed. Okay. Sometimes it does. So we've got this stuff down where there's 2 things we need to finish up with. Okay? Number 1. What if it takes on a circular path? How do we make a parametric representation of the circle? So we got to review that, and we just covered it in my Calc 2 class. But it's going to be a long time before those Calc 2 students are doing this right here. And so, it might be forgotten. But we're about to encounter this. I'm doing a problem like if you look at the sheet number 15, and they want you to compute the work done by, here's the force field. So when they want you to compute the work done, find the work done by the force field. Find the work done by the force field to move a particle, just to finish this out, that moves once around the circle x squared plus y squared equals 16. Oriented in the counterclockwise direction. So I'm just going to put counterclockwise in parentheses. Let's draw that. Okay, you can start wherever you want and stop wherever you want. Hardest part to this problem, parameterize. You need to parameterize this. We need to make a parametric representation of that circle. How do you do that? We use cosine and sine, okay? And when we use cosine and sine, the only thing is we need to know the radius. So here's the hardest part to this problem. What can I call this? I want to call this R of t, and I want to know what to put here and what to put here. By far the hardest part of the problem. We use cosine and sine. What's the radius though?
4, right?
This will do it. A 4 cosine t and a 4 sine t. I want you to step away so you can all see this, so that you can parameterize any circle you want centered at the origin. It all depends on the radius. Everyone, do you want to know why I put cosine before sine? That makes it move counterclockwise. It does. You go, how do you know? Oh, you can explore it. I know it's something back from a Calc 2 class, but you can plug in points, like what's going on at t equal to 0. And then see what's going on at t equal to power 2. And you'll see this thing will move which way? Counterclockwise. So the movement is now important. So cosine before the sine in this representation will make it move counterclockwise. And what would make it move clockwise if they say clockwise?
Sine.
Just put sine before cosine. And if you don't believe me, you can go, let me just explore a table. Make t values, make x's and y's, you will see it moving that way. Cool. So any questions on how to parameterize any circle we get? I love it. That's what we'll do. Radius in front of here, it's going to work. So there's our key. We'll do the r prime key. What's the vector field in this one? And when the vector field is, here it comes. So we're going to evaluate, find the work done. Well, what is the vector field? It looks like it's y comma negative x. Okay. There's your vector. Now, if you and I had an image of what this vector field looked like, we'd know if this answer comes out to be positive, negative, or 0, right? I think we saw one of these earlier, but I forget what it looks like. So let's just do all the math. Here we go. First of all, I'm already stumped. I got to do a full loop, they said, once around. Any suggestions on the limits? It's got to be in terms of t. What do y'all think? 0 to 1? No, that's not going to cut it. That would be 1 radian. 0 to 2 pi, way to go! So if you ever have to do one loop, just go 0 to 2 pi. All right. F composed of r of t dot r prime of t. Well, let's do F composed of r of t. Y comma negative x. That's the y, that's the x. So we'll go